Hello, I am Stephen Wheat, and I am here to discuss how QCT's QCT POD is designed to aggressively address the uncertainties and complexities of developing advanced heterogeneous architectures to take your HPC and AI performance to a new level while reducing your overall system management burden. Traditionally, applications have relied on numerical methods for computing on high-performance computing (HPC) infrastructures. These were run on collections of HPC nodes of a common homogeneous architecture, as we see here on the left. Now, people find that each of their workloads may better be served by different chip architectures. The workload diversity continues to evolve as researchers find ways to utilize accelerators to enhance their applications' capabilities and/or performance. This means that the need for diversified compute or heterogeneous systems is increasingly more prevalent and important. Today, we see more users running applications with accelerators, such as GPU or data processing units, DPUs, within HPC systems, as on the right. This gives rise to heterogeneous architectures. Designing the right heterogeneous mix is complex, but it can be made easier with system platforms that provide a consistent and optimized infrastructure that avails the performance of each of the constituent architecture building blocks to the application suite. As mentioned earlier, designing a heterogeneous platform versus a homogeneous platform involves a greater complexity in design, sizing, and software programming methodology, where the different compute nodes have their own software ecosystem. The system design model is made more complex by the consideration of an institution's runtime environments for various applications. These runtime environments consist of bare metal, virtual machines, or containers. There is a logical reason for each, and frequently, users desire to support all these environments simultaneously and seamlessly. In addition to the compute components, the network or fabric needs to seamlessly support each of the application's runtime environments. We also find the workload characteristics of the applications within a workflow can be quite different. They can be CPU intensive, memory intensive, or I/O intensive. While each different compute engine has its own instructions and compilers, it gets even more complex as they need their own libraries and programming models. The key question is how to provide for effective runtime for each application on such a diverse architecture. Throughout numerous projects, QCT has developed a workload development process to tackle these challenges of the heterogeneous environment. Experience with AI and HPC has enabled QCT to design a converged environment with a flexible infrastructure to effectively scope and deploy heterogeneous systems that comprehend an end user's application needs. HPC is associated with compute-intensive workflows, while AI tasks are more data-intensive. These workflows require different environment settings, and QCT finds mutual benefits and brings them together to resolve the customer's complex issues. QCT improves AI training through HPC parallel computing architectures, and HPC workloads can achieve improved performance with GPU, DPU, or FPGA acceleration. This is a diagram of how QCT works with customers to continuously deliver state-of-the-art solutions with a deep understanding of the customer's workload. QCT can accurately integrate the best-fitting hardware and software infrastructure. Through system tuning and optimization for the target workloads, QCT aims to build a workload-driven design environment for users. We'll note that this is a system that also continuously improves as we go through it cycle after cycle. Following that philosophy, QCT has developed the QCT Platform on Demand system design called QCT POD. The QCT POD is a workload-driven, fully integrated system design. In QCT POD, QCT provides a best practices-based integrated hardware and software system for specific workloads. QCT POD is a converged system for AI and HPC. It has flexible compute, storage, and networking building blocks to do HPC simulation or AI training. It also includes cluster management tools to simplify the deployment, monitoring, and management process for administrators. It also has a built-in development environment to optimize the workflows for AI training. The whole system is a pre-validated and pre-configured rack-level system designed to start working upon arrival and installation. The QCT POD deployment function simplifies the deployment process with automated processes. Users can finish the installation process by simply filling in some information and clicking. With just a few simple steps to select various configuration parameters, the user initiates the final system deployment and automatic installation. QCT has demonstrated that the deployment process can be shortened from days to hours, even for large-scale deployments, which saves time and instills confidence in the solution. With our technology leading and quality-oriented R&D team, we optimize AI HPC workloads from the lowest, most intricate layers and up. This includes the BIOS, the OS kernel, libraries, compilers, runtime environment, and the application layer, doing all this across different application types. We find the best practice of the system design and deliver optimal turnkey performance for our end users. This comprehensive approach helps to reduce the time of integration and the system starting its production work, as well as optimizing for the runtimes of each job. In the following slides, we will review some example use cases. In these next few slides, we will illustrate a real use case example of heterogeneous compute architecture by showing our testing of VASP on a GPU acceleration with workload tuning. To give a background, VASP, the Vienna Ab Initio simulation package, is a widely used application for molecular dynamics. It is applied to many different applications. Some of the examples are bioscience, in which VASP can be used in the study of the genetic causes of diseases. It can also be applied in the energy domain to discover new energy types. And it can be used in material science to help study, for example, the conductivity of a new material. The parallelism of GPUs combined with the gradually matured software ecosystem, like OpenACC, have provided an alternative to the CPU-only solutions, with their performance bottleneck for such CPU-intensive codes. However, GPU acceleration alone can only provide a limited performance boost. The key to have a significant performance boost is to combine GPU acceleration with workload tuning. The BIOS settings, OS, application libraries, and compilers should all be configured for the specific algorithms, and workloads to produce optimal performance. A deep understanding of the workloads and system is required for workload tuning. QCT's performance team is composed of workload and system experts that work together to build QCT's workload tuning capability. Together, they build the automated processes to do final configuration of the QCT pod for a given user's needs. QCT has tested 4 important algorithms that are commonly used in VASP to show that significant performance improvement can be achieved by GPU acceleration combined with QCT's workload tuning methods. As illustrated by these graphs, the verticals show the performance speedup. The blue bars represent the performance of only using CPUs, and the green bars represent the performance with GPU acceleration and QCT's workload tuning. Overall, there is a 5 to 9-fold performance improvement with 4 GPUs versus the CPU only. The system used for testing is QCT's AMD-based GPU server, the QuantaGrid D43N, which supports up to 4 NVIDIA A100 GPUs. Here's another example of performance improvement. This is for how AI-enhanced pathology analysis achieves greater performance by using GPU acceleration and workload tuning. QCT has worked closely with aetherAI to deliver an end-to-end AI medical solution. aetherAI provides an AI-based model for pathology analysis with more accurate prediction rates and better performance. Aether worked with QCT to further increase the performance of their AI model with GPU acceleration. QCT also helped to determine the optimized system configuration for the workload. As a result, as shown in the graphs, the processing time has improved significantly from this approach. The throughput has also improved significantly. The result is that more images can be analyzed in the same amount of time, along with greater confidence in their analysis. A key design principle for QCT POD is also to simplify the system management, thus reducing the system administrator's operational burden. To fulfill this principle, QCT POD provides a web-based dashboard for administrators to check the resource utilization of CPUs, memory, disks, and GPUs in both bare metal and container environments. It can also detect and alert them to system anomalies. QCT POD also provides key capabilities such as automated resource management and job scheduler functions, account management, and high availability functions, all in an integrated container orchestration platform. QCT POD simplifies cluster system management, but also gives the administrator full control of the entire system. Reviewing the features and values of QCT POD, we find that it is a rack-level, workload-driven, integrated design system that helps users mitigate the complexity to adopt a heterogeneous system. On top of that, QCT POD provides an easy-to-use centralized management and monitoring dashboard to simplify deployment and management of the cluster. All this can be easily scaled out based on the modularized architecture design. Overall, QCT POD can speed end-user time to value for their AI and HPC deployment. In summary, heterogeneous compute architectures help to resolve the performance bottlenecks that have risen and are rather hard to surmount with just CPUs. There are still challenges that come with heterogeneous designs that need to be handled. QCT offers QCT POD to significantly ease the transition from a homogeneous CPU-only model to the more rich, heterogeneous accelerated compute model. QCT POD reduces the management burden in a unified system architecture. We reviewed serious examples of workloads that had significant improvements with GPU acceleration when combined with workload tuning. QCT is an expert in doing this. QCT POD brings this expertise in a turnkey solution to you. Thank you for attending this session. For more information, please navigate to www.qct.io. It has been a pleasure to host this session. Good day.